So we're going to let f of x equal x squared minus x, for x is the element of all real numbers. The following diagram shows part of the graph of f. So as you can see, we see part of the graph of f. The diagram's not drawn to scale, so you can't base it off of exactly what it looks like. You kind of got to base it off of what you can prove. The graph of f crosses the x-axis at the origin in the point 1, 0. Show that f symbol 1 equals 1. What does that symbol mean? What does that symbol mean? It means the derivative. So we have to show that the derivative of 1 equals 1. Remember, in any show problems, you have to do the mathematical process to get that answer, okay? So if f prime means derivative, that means we need to find the derivative, okay? And somebody online, what's the derivative of x squared minus x?
2x minus 1.
It's 2x minus 1. So then we want to make sure that we do that. And then to actually show that f prime of 1 is equal to 1, what should I do? I need to plug in that x value of 1. So that gives me 2 minus 1, or sorry, 2 times 1 minus 1, 2 minus 1, which is indeed 1. Then it says line L is the normal to the graph of f at P. The normal. What does normal mean? Not tangent, it's related to the tangent though.
The reciprocal?
It's the opposite reciprocal of the tangent. When we found, or when we showed that f prime of 1 was equal to 1, we found the gradient of that tangent line. But it says that the line L is normal to the graph of f at P. And normal is opposite reciprocal of the tangent, okay? So then that means that the gradient of the normal is going to be equal to what? Somebody online?
-1.
What's going to be the gradient of my normal line?
-1.
It's going to be -1, okay? Because it's the opposite reciprocal of that purple line which I drew, which was the tangent. So then we have to find the actual equation of that line. Remember, to write equations of lines, all we need is a gradient, which we have, and the point, which is P, is shared on everything. So then we can use P and 1 to write the equation in this particular form. Remember, this is old school right here. Okay, you plug in 0 for y, 1 for x, and a represents your gradient. So then the value of b is going to be a positive 1, which means my equation for line L is -x plus 1. Questions? So line L intersects the graph of f at another point Q, as shown in the following diagram. Again, the diagram's not drawn to scale. You have to find the x coordinate of Q. How would I find the x coordinate of Q?
Set the normal and the quadratic equal to each other.
That the normal and the quadratic equal to each other. Exactly, because you're trying to figure out where two lines intersect. If we had our calculator, that's what we would do. We would do L1, the quadratic, L2, the line, see where they intersect. Essentially, you're finding out where they equal each other. So this is nothing but a good old, oh, we forgotten? How many times did I say that last year? I need to solve for x, and this is nothing but a good old, oh my Lord, y'all, quadratic. It's a quadratic. Y'all don't remember that? How many times did I do that? It's nothing but a good old quadratic that we just need to solve for. Get everything to one side. If I add x over, the x goes away. If I subtract over the 1, I get x squared minus 1 equals 0. This can be factored into what?
X plus 2, x minus, x plus 1, x minus 1.
X plus 1, x minus 1. When I set them both equal to 0, I'll have x equals a negative 1 and x equals a positive 1. Which one represents the x coordinate of Q? The negative 1, because I knew the x coordinate of P was the positive 1 from earlier in the problem. So since that's a negative 1 for Q and P is at positive 1, it's asking me to find the area of the region enclosed by the graph of F and the line L. This is what you guys watched the video on last week. You find the area in between two curves. The formula for the area between two curves says the integral from the start of the area to the end of the area. And then in the actual integrand itself, it was what? Who remembers?
y1 minus y2.
And what did y1 represent? The curve on top. And then y2 represented the curve on the bottom. As we can see, the curve on the top is the line, and then the curve on the bottom is the quadratic that encloses that area. So then it's going to be my line, which was negative x minus y, minus the curve on the bottom, which was the quadratic of x squared minus x. That's how we would set up the integral, so that way we can find the area between two curves. So it's from the start of the region to the end of the region. That represents your bounds. Then it's the top curve minus the bottom curve every time, okay? So of course, from here, I am gonna need to simplify some, okay? I need to make sure I distribute over that negative. That's why I put it in parentheses. Oh, sorry, it should have been a plus. Thank you for that correction, because my normal was a plus 1. Thank you for that catch, because I wouldn't even know what the wrong answer. So it's negative x plus 1. Distribute over that negative. Combine my like terms. So I have negative x squared. Yep. Plus 1 dx. Making a lot of minor mistakes. And these are minor mistakes are definitely something that you guys can make. So just double check, make sure that you go back and you're not forgetting a symbol anywhere, you're distributing incorrectly or anything like that. Now here we apply the fundamental theorem of calculus, which says we need to take the integral of negative x squared plus 1. Someone online, what's the antiderivative of negative x squared plus 1?
Negative 1/3 x to the power of 3 plus x.
You kind of faded out at the end. I heard negative 1/3 x to the power of 3
Plus x.
plus x. There we go. And I'm going to evaluate that from negative 1 to positive 1. Remember, with the fundamental theorem, which bound do I plug in first? The top one. So that's negative 1, or sorry, negative 1/3 times 1 to the third plus 1. Then I subtract it from what I get when I plug in the bottom bound. Again, symbols left and right. So then it becomes negative 1/3 plus 1. On the inside of the parentheses, negative 1 to the third power is a negative 1. Times a negative 1/3 is a positive 1/3. Minus 1. Turn to a negative 2/3 plus 2. So then my final answer for the area enclosed by the graph of F and the line L would be 4/3. The new part that's integrated in is the fact that now instead of just finding the area between the curve and the x-axis, we now have the formula to find the area in between two curves now, okay? And remember, the bounds are from the start of that region to the end of that region. That's why it was negative 1 and positive 1. and then it was your top curve minus your bottom curve that actually encloses in that region. Everything else we've been doing with integration, okay? It's a three-parter. To practice, we're going to sketch the graph of y equals x minus 3 and the graph of x squared minus 3x on the same set of axes. We're going to find the coordinates where they meet and then find the area of the region enclosed by the two graphs. So when we look at this one, it says the shaded area is 2.4 units, find k correct to 4 decimal places. Well, the truth of the matter is that the shaded region, which represents 2.4, is just this area right here. And we don't know how to go about finding the antiderivative when we have just a line and a point that enclose the area. But because this is a quadratic, it says so by x squared, we know that if this area is 2.4, then we know that this area over here is 2.4. And so then we can use that to help us find the value of k. Because now I have from point to point an enclosed region. So to figure out what these two x values are, I want to set the quadratic equal to the linear function and solve. When I do that, I end up taking the square root of both sides, and I'll get plus or minus the square root of k. So then those two values represent the lower bounds of my integral. So from negative square root of k to positive square root of k, where the line is on top and the quadratic's on the bottom, the area between the two curves should equal 4.8. Not 2.4, because I'm now going from point to point, and the entire area enclosed is 4.8. When I take the antiderivative of a constant k, it is because the constant times x, and the antiderivative of x squared is 1/3 x to the third. We are going to evaluate this from negative square root of k to positive square root of k, and again, the area should equal 4.8. I'm going to plug in my upper bound, which is the square root of k. And then I'm going to subtract it from when I plug in the lower bound, which is a negative square root of k. Lots of k's here. And again, this entire area, when I evaluate the definite integral, should equal 4.8. Now, the reason this is the calculator problem is because from here, I need to plug in the left side into y1 and the right side into y2. Remember, on an IB exam, never put y1 and y2 on your paper. That's calculator notation that's frowned upon, okay? Just know that at this point, you want to actually go into your calculator, plug the left side of that equation into y1, then plug the right side of that equation into y2, like so. Then you'll want to graph it, and we're looking for that intersection point. I replaced all my k's with x's, and so now I'm looking for that intersection point. So I'll click second trace, option 5, move close to that intersection point, and click enter 3 times. And the value of x is my value of k, and I'm rounding that to 4 decimal places, so that's 2.3489. 2.3489. The last one I want to do is this one. It does incorporate a little bit of trig, and so I want to make sure that you guys haven't forgotten how to do this. The illustrated curves are those of y equals sine x and y equals sine 2x. Remember, sine x has a period of 2 pi. The curve that shows one complete cycle from 0 to 2 pi is C2. So C2 equals sine x, which means that C1 is sine 2x. Remember, the 2 is a horizontal shrink by 1/2. It also changes the period to be pi instead of 2 pi. To algebraically find the coordinates of A, again, you're looking for that point of intersection. So you want to set the two equations equal to each other. Definitely wanted to do this one because I wanted to refresh your memory on how to solve these types of equations. Remember, sine 2x is a identity that can become 2 sine x cosine x. So then I can subtract over an x. Remember, I never want to divide by sine. I'm sorry, I want to subtract over sine x. I never want to divide by sine, because when I do, I end up losing a solution. Instead, if I bring it over to one side and factor out, it will allow me to find all my possible solutions. When I set both factors of sine x and 2 cosine x minus 1 both equal to 0. Sine equals 0 at 0, pi, and 2 pi. And then when I solve for cosine x, I'm looking for where on the unit circle does cosine equal 1/2, and that occurs at pi over 3 and 5 pi over 3. Now the one I'm most concerned about is for the coordinate of a, and as you can see, a is located before pi, and the only solution I have that is before pi is pi over 3. To find the y coordinate, I want to plug it into either sine x or sine 2x, and then find that sine of pi over 3 is equal to a square root of 3 over 2. And that's my answer for B. Now to find the actual area that is enclosed by C1 and C2, it is split up again, just like before. Okay, anytime the area between two curves changes from one curve being on top to one curve being on the bottom, you want to create 2 or however many integrals. So from 0 to that x value of a, which is pi over 3, C1 is on the top, C2 is on the bottom. So this integral represents that first little bit. But then from pi over 3 to pi, C2 is on the top and C1 is on the bottom. So anytime the curves change from one being on top to the other one being on top, you have to split the integral. Then from here, I just apply my definite integral, my fundamental theorem of calculus, to find the actual area enclosed by C1 and C2 from 0 to pi. The antiderivative of sine 2x is a negative 1/2 cosine 2x. Remember, that's one of your linear factor formulas. The integral of sine x is a negative cosine x, but 2 negatives make a positive. I'm going to evaluate that from 0 to pi over 3. And then on the other side, I keep going. I'm going to add the antiderivative of sine x minus sine 2x, which is a negative cosine x plus 1/2 cosine 2x. And that will be evaluated from pi over 3 to pi. Remember, when evaluating your integrals using the fundamental theorem of calculus, you always plug in your top down first. And subtract it from when you plug in your lower bound. Same thing over here. Plug in our top bound. Subtract it from when I plug in my lower bound. And using our knowledge of the unit circle, the cosine of 2 pi over 3 is a negative 1/2. The cosine of pi over 3 is a positive 1/2. The cosine of 0 is 1. The cosine of pi is a negative 1. The cosine of 2 pi is a positive 1. The cosine of pi over 3 is a 1/2. And the cosine of 2 pi over 3 is a negative 1/2. Lots of signs. Be careful not to make any errors. Negative 1/2 times 1 is a negative 1/2. Add 1 gives me a positive 1/2, so I'm just going to have a minus 1/2 there. That becomes a positive 1 plus 1/2 minus a negative 1/2 times a positive 1/2 is a negative 1/4. When I add a negative 1/2, that's going to give me a negative 3/4. But then that negative is going to make it a positive, so I have a positive 3/4. Then when I combine 1/4 and 3/4 is 1. These negative 1/2, this 1/2 and this negative 1/2 cancel out. Then I'll have plus 1 plus 1/2. So my final answer is 2 1/2, which is 5/2. So the area between the two curves is 5/2. And that's how you do the area between two curves. When the integrals are split up, like in this particular case, and then one where I wanted to kind of do one where I already gave you the area, you had to find one of the curves themselves. Okay? The other problems that we did do today that I did not record, this one was a very simple one where you had to graph two functions, find the coordinates of where they meet, so you just set the equations equal to each other, and then find the area between the two graphs. This one's a fairly simple one, it was non-calculator. And then this one here, you had to write the integrals as the sum of two definite integrals, using your calculator to find the intersection between the cubic and the linear function. And then again, continue to use your calculator to find the area of the shader region.